tock, tick tock, tick tock, tick tock. Here we are. Okay, thank you everyone for joining in. I realize this is a bit of an imposition, but it's important for us to stay on track at this point. And if we take care of this today and tomorrow, it means that we're going to be all together for the important part of our semester. In some ways, this part is the hardest part because it's getting accustomed to the new software environment and getting our minds around some things that we know in theory, but somehow can look much different in practice. All right. And that's really why it's so important for us to march along for the first half of our semester. And then in the second half, we get more flexible, we get looser, we get more options to pursue our interests. But for right now, it's important for us to stay together. And that's why we've got to make up for these Thursday holidays. And we do it this week. We are just right back on track. I realize this is an imposition. I know that at least one group today and one group tomorrow are bopping out, are just, closing one meeting and opening another. And trust me, I'm doing the same thing today. And so I know what it's like, but let's just do it and keep moving forward. But I won't keep you that long today. All right, we'll try to keep this down a little bit. And because what we want to do today is basically just a little bit of review and reminder about some theoretical topics that you have encountered in a prerequisite to this class. All right, an introduction to networking class. We just want to talk about encapsulation and the protocol stack, the network protocol stack, and just pull this back to the front of our minds because on Thursday, this is going to be completely front and center when we work with it in practice. We're going to just need this theoretical foundation so that we can get our minds around why we're doing what we are doing when it comes to configuring the servers on our network. So, if you're from Lab 4, you're welcome, but this is review for you because we talked about this earlier, all right? And Monday Lab has been uninterrupted. It's the Thursday scheduled lab that is what we need to, shall we say, replace or recover, all right, to make sure that we're all moving at the same pace. Yeah, no, man, it is a replacement class, but it's not a replacement class for Monday. It's a replacement class for, what was it? 16th of September, Sarawak Day, East Malaysia Day, Malaysia Day. Oh, they don't call it East, sorry. I don't know. Too many of my friends kind of corrupting my vocabulary here. But never mind, yeah. It's to commemorate 1963? Yeah. It's not that you're not supposed to be here, it's just that you don't need to be here very definitely. Supposed to be here? Alex Schmidt, you're always welcome. All right, so let's turn to our review. The one tomorrow, there's another one tomorrow that is going to introduce a topic that's a little bit new. All right, I think everybody's got an idea about DHCP. I'm sorry, about DNS. And I think everybody's got an idea about DNS, but DHCP might be a little bit new. But let me just put one thing in here first. Okay. First thing is, by Thursday, you need to have your 2-clone VM configured to things first. All right, and that makes, we're a little bit sideways on this one in a sense, because we talked about that first things first configuration on Thursday. All right, but we're gonna this week Thursday, it's going to be assumed that you have reached that point, and we're going to talk about taking that 2-clone machine and replicating it to be our other servers. All right, and that means that if you are that far along, if you have got that part done, everything goes super smooth. All right. If you haven't, then you're going to be a little bit taken aback. All right. Because, Schmidt, again, we're in this phase where we need to be stepping forward step by step. All right. And working all in synchronization, march, all right, to achieve our initial objective, which is to have our base system ready by the time of the semester break. All right, so let's, again, what we're doing today is we're reviewing some concepts that you definitely encountered in a previous class, but we need to bring these back front and center, all right, so that when we step forward tomorrow and step forward on Thursday, we understand the why of the what. All right, we're going to be configuring our servers. We need to know why we're doing it this way. All right, so we need to think about our subnetting architecture. All right, and we need to think about our name servers and our IP addresses and how all of these things fit together invisibly in the background as part of the theoretical framework. Terms that we're going to use, and again, assuming you are actually familiar with these terms, all right? But again, just bringing them front and center, part of our developing our mental attitude, if you will. All right, so this ISO model, it's standard stuff in these modern times because it was developed. You got to put yourself again, think in the mindset that there's people behind this, and this ISO model was developed because people didn't know how networking should work. Right? Nobody knew it. They were inventing it at the time. And this was the way they got their minds around how the network is supposed to work. Sadly, perhaps, they took it to the ISO. And when you take things to the ISO, all right, it means that it goes to a lot of committees. And it comes out in some ways to seem a little bit extra complicated. All right. I hope you can see this because I just switched into presentation mode. All right. Maybe I should not do that. Just presentation mode. Let's just get rid of that one. All right. So the idea is to stack 7 layers. All right. It's got a nice recursive name. It's the ISO, International Standards Organization, OSI, backwards, ISO backwards, Open System Interconnection Model. The idea is that the application layer is at the top and things flow down the stack and then get transferred across the media here at the physical layer. And then we're back to the software layer. All right. Some people like to draw a dotted line right here between data link and network and say data link and physical are computer engineering because they're owned by the IEEE, the Institute for Electrical and Electronic Engineers, all right, where network, transport, all of the rest up here, that's owned by computer science, all right, because that's the ISO and the IETF. But we're not going to get into that kind of politics. Please do not throw snow peas away. Right? Just a simple way to remember this. All right? But one lovely thing is that nobody worries about layer 5 and layer 6 anymore. All right? But we do talk a lot. We talk a lot about layer 2, layer 3, layer 4, and layer 7. And we use those terms, okay? Because actually the TCP, if you look back at the history of it, the TCP IP model was worked out in 1974, 1975, 76, and the OSI model was 76, 77, 78, and that's why they don't quite match up, because they took the TCP IP model, which was a small research group that worked this out. Well, actually, a fairly extensive research group, but relatively small compared to the committees at the ISO. And they were the ones that made the 7-layer model. All right. So 2, 3, and 4 roughly correspond. And that's why we talk about 2, 3, and 4 all the time. 7 application and 5 in the TCP model have the same name, but it's just general convention that we talk about layer 2, 3, and 4 as if we were thinking about the ISO model, and everything above that is layer 7. The other thing on this diagram are those yellow boxes, okay? SSL is something that we're concerned about the second half of the class, all right, after the semester break. But TCP, IP, and Ethernet, these are things that we need to have in our mind as we configure our network interfaces, as we configure our servers in practice. All right, so that's really one thing that we need to really focus on today. Presentation layer, session layer, completely widely ignored, but in case you're curious about what they are, according to the ISO definition, there's your explanation. But we don't need to worry about them because really nobody does. This concept, though, is really important for us because this is an abstraction of what is actually happening. Okay? What's actually happening is counting bits, and how those bits get counted is done using this basic template, this basic template for interpreting the bit stream. The bit stream is the beauty and joy of computer science. It's everything in computing. It is the thing. That's all we have to work with. And we just lay a template over the bit stream in order to interpret it. And that's how we distinguish between a Word document, an Excel spreadsheet, a GIF file, a PowerPoint, a Teams message, whatever we have. It's all about just laying a template over the bit stream. Now, cultural sensitivity here. All right. Engineering, the people who are writing the standards need to be exact, and so they invent their own terms to, make it easy for the people to read who are reading the documentation to remember which level we're talking about. All right, we're going to elide all of this together and just use the term packet. But never mind, we need to know that there are formal terms, and sometimes people will be using these formal terms rather than eliding them all together like we do. So here's the concept, and the important concept is encapsulation. All right. As a packet moves down the protocol stack, it gets bigger, all right, because each layer adds a little bit of information to that bit stream, all right, so that when it gets to the destination, the process is easily reversed, all right, and that's really all we're talking about when we talk about moving up the stack or moving down the stack. All right. I've got a better diagram here in just a minute. So again, we're all focused on layer 4, TCP, transport layer, layer 3, internet layer, and layer 2, all right, the data link layer, or again, we're going to fuzz up our terminology here and always call this one the Ethernet layer. We're going to, or layer 2, it's going to be layer 2 or the Ethernet layer. It's going to be layer 3 or the network layer or the IP layer. It's going to be layer 4 or TCP layer. Just a stream of bits. It's all about counting the bits and trying to make sense out of it according to how the protocol is defined. So when we say the frame header or the datagram header with a segment header, right? We're just talking about taking a stream of bits, which is the data part, and adding some more bits onto the front. And the standard tells us how to count the bits and interpret them. All right? Now, again, we're not digging into the details, but we must know the key information in each of these headers. All right? So the key information that we will try to take advantage of in practice at the Ethernet layer, layer 2, is the MAC address. This is the one that is in the burned onto the chip in the Ethernet interface that's installed on the motherboard in our device, whether that device is our tab or our phone or our laptop or our desktop or whatever we have, all right? That MAC address is unique to the manufacturer and the item that they have manufactured. Now, that's a complicated job, but there's plenty of competent people who are taking care to make sure that each of these MAC addresses are unique. But the important point for us is as this bit stream gets received by the destination, we can count the bits and come up with 48 bits of source address, 48 bits of destination address, and process those to decide if this message is for me or if it's for someone else, and make a decision like that. This same pattern, think of this as a design pattern if you like, moves up the stack to the layer 3, the IP layer, all right? Source IP address, destination IP address. Difference, huge difference here. MAC address is part of the hardware. It's a characteristic of the hardware, an attribute. IP address is arbitrarily assigned by a system administrator, human intervention, if you will. All right? And we need to match some way an IP address to a MAC address, and that's what we're talking about tomorrow when we talk about core services for our networked system. All right? So layer 2, source and destination MAC address. Layer 3, source and destination IP address. Layer 4, it's a port. A port is an operating system concept. All right? We saw this when we looked at the task manager and did the services tab. Port is just a number that the operating system uses to keep track of who conceptually is listening. There's a service that is listening. It has a port number associated with it. So when the bit stream comes across and it moves up the stack, the operating system can count off the Ethernet header and discard it, count off the IP header and discard it, and look at the TCP header and decide which process to pass the rest of this message to. and it knows which process it should pass it to by checking the destination port. Pardon me. When we talk about moving down the stack, again, this is the reason they worked so hard. Brilliant minds working so hard. The nice thing about this is that it makes it so easy to make the response, because you just take the bit stream that came in, and for the response, when the packet goes out, you just flip. Destination becomes source. Source becomes destination. It's an easy bit manipulation that can be handled very quickly by the CPU. And you've got all of these headers ready for the response as soon as you get the request in. So here's the way it looks in ISO speak. All right, PDU, Protocol Data Unit, SDU, Segment Data Unit. All right, and again, we don't want to get bogged down in this, but sometimes these boxes and arrows diagrams can help us get our minds around it. All right, but at the bottom here, it's always the bit stream, and all of this is done just by counting the bits, right? So that they correspond to the template that they've laid over it. Perhaps easier, right? An easier way to look at it is the questions that are asked, and in practical sense, this is what we need to know when we're configuring our network interfaces. Right? When the bit stream comes across, it reaches the physical hardware. And the physical hardware has the counters in it. When it counts off a certain number of bits, it passes it up to layer 2. Right? Layer 2 gets examined and says, is the destination my MAC address? All it needs to do is count this far into the bit stream, count off 48 bits, compare it to the ones that it has ready. All right. If the answer is yes, if those match, then you keep processing. Otherwise, you forget about it and go on to the next one. All right. When you pass it up, 2 questions here. Am I a router? Talk about routers in just a minute, all right? But a router is one that redistributes packets at the IP layer. Whether or not you are a router, if this is my IP address, pass it up to the TCP layer. All right? TCP layer, again, just counting the bits. Find that destination port, operating system, hello, match it up. Does this match a service listening on the port? Okay, if yes, it gets passed up there and the application layer takes care of it. All right? ISO, it's 5, 6, and 7, but we don't worry about that. We just lump all that together as layer 7 and let the application take care of it. If not, send it to the bit bucket, all right? Or maybe send a undeliverable response. Ooh. It is below our Now, you know, I honestly, yes, I should have a better answer for that question. But seriously, this is not the sort of question that we need to be concerned about at our systems and network administration level. I'm really going to apologize for that, but it is not the sort of question that we need to be able to answer as part of our scope. All right? We stay at a level above that. All right? What you're asking about here is Ethernet frame level, stream of bits, bit counting. Okay? All we're concerned about is this an Ethernet frame? Is this my MAC address? This is actually where we're starting. All right? You're asking about the question of, is this an Ethernet frame? And that to us is something that is somebody else's job. It's below our event horizon. The place where we start is this my MAC address? That's where we start, all right? And that's our event horizon. Everything else below that, somebody else takes care of it. It's a good question, right? But now it's Matt. Otherwise, we don't need to and don't want to get too into those details because we have, as they say, other fish to fry. All right. And again, the idea here is that at layer 3, if we're working across parts of the network, and this is where we're thinking about subnets and making a more complicated network than just local machines wired together. All right. The intermediate hardware, all right, only works at layer 2. That's when it's called a router or a gateway, right? A switch or a hub works at layer 2. Right? A switch or a hub is Ethernet hardware. A router is IP layer hardware. Right? What they're doing is just rearranging some of the bits in the packet, right, so that they can move from one point to any number of intermediate points. That's why we always picture the internet as a cloud. There are any number of intermediate points between the source and the destination. But they only examine that bit stream up to either the source and destination MAC address. If it's a switch or a hub, you only look at that bit stream up to that point. You count out those number of bits and focus there, right? Or if it's a router, it gets past the Ethernet layer and looks at the source and the destination IP address and manipulates those and the IP packet header flags in order to get this packet one hop closer to its actual destination. And that's where we get into the practice of things. All right. when we set up our network architecture, and this network architecture is pre-configured so that we don't have to make too many decisions and do too much to get this actually working, all right? Big parts of this are configured already. So we just need to do some edge margin adjustments to get this working. Partly that's because, we want to keep focused on the big picture. And partly because there are just so many decisions to be made, it's good to work with a pre-configured example, all right? So Thursday, when we start taking our 2-clone machine and clone it off and create one called Gateway and one called the LDAP server, web server, mail server, all right? We're going to set up the Gateway so that it has 3 network interfaces, so that our subnetted network architecture, we're going to have it configured so that this web server cannot communicate directly with the LDAP server or the mail server, right? Our gateway is going to have an interface with an IP address assigned to it that allows direct communication with the web server, all right? And it's going to have another separate interface that's configured that allows direct communication with the LDAP server, and another one for the mail server, all right? And anytime that this one wants to communicate with this one, it means it has to cross the gateway. And the reason we do that is because that is, in practice, the way the global internet works, all right? We could have as many gateways as we like, and indeed, when we're doing this right now, there's a lot of network between me and the Microsoft Cloud and you and the Microsoft Cloud, all right? But that's all the intermediate parts, and this whole process is going on over and over again. And sometimes when we look at it this level, it looks so complicated. We can never imagine that it would work, but experience and practice shows that it actually works very quickly, very nicely, and very smoothly after all of these decades of very clever people devoting their minds to making this system work. So that's why we want to do it in a small sense, right? So we can join that clever crowd that works very hard to make these systems work. Just check the time here. Okay. So VirtualBox in the middle, all right, provides these network connections, okay? A layer 2 hub kind of access, and the gateway provides this layer 3 communications between our servers based on the IP address, based on the subnet. Now, I know you've heard about subnets, but hearing about them and knowing about them in theory is one thing, and when we're doing it in practice, it adds a kind of a whole layer of complications for us to take care of. But that's just what network administration is about, is understanding the dimensions of it. And this is just one dimension that we need to be conscious of and get properly configured and take care of. All right. So I think we can kind of slip by this one. All right. Just a note on the symbolism, the symbolic representation. All right. Again, it's about counting bits. All right. Talk about the network part of the address and the host part of the address. Again, we're just laying a template over the bit stream to decide what's the prefix, the network part, and what's the unique part for the host. And the way we do that is called a net mask. All right. And we use very simple net mask. And the classic representation is the first one here. All right. And the way to read this is same, same, same. 255, we read that as same. 0, we read that as any. All right, so what this net mask says is that, sorry, every message that comes in from with the same 192 and the same 168 and the same 11 is something that we should be listening to. No matter what's in the bottom part here, last part, right? Same, 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 any. All right? And we can move that around and manipulate it a little bit so that it can be same, same, any. All right? But this is what the convention is for subnetting. We use what they call the subnet mask, all right, to decide, to make those decisions about should I pay attention to this packet or should I discard it. Now, 255 is 8 bits in decimal number. All right, in a hexadecimal system, it is double F, right? Double F, and it's kind of an exact representation of the bit pattern. It means 8 ones. And lots of people like to shorten that representation and just show the number of bits up front that are all ones. And that's the other representation here, stroke 24, all right? 8, 16, 8 plus 8, 16, 16 plus 8, 24, all right? It's the alternate expression of the same thing. And we'll be seeing both of these in practice, so it's important to recognize them for what they are. All right. So here's the thing. When I have my gateway here, it's called Delta in this diagram. It's got 3 interfaces, each one with its own IP address, 16.20, 16.30, 16.40. All right. That means that Delta can communicate directly with Alpha, Iota, and Beta on 3 different interfaces. And it's got the software to say, all right, comes in on this one, destination address. It's not for me, but I am a router, so I pass it out one of the other ones. So I'm a center point in the communications between these different machines. All right? And again, it's a simple example, and it's sometimes simplifying it makes us wonder, why do we do this? We do this because this is exactly what Microsoft is doing when it's taking in my source from unify.com and passing it out on your Digi or whatever you have. I mean, some these networks can be controlled by completely different people. Okay, we just shrink it down so that we get how it works, right? But it scales up. Well, it actually in practice it scales up to the global internet. And again, that's why the TCP, the ISO, this layered network protocol model has proven itself over the decades to be an elegant and workable abstraction. Ooh, let's skip over VLANs again, just here for completeness. Okay. Let me just check the time here. Let me just check what we've got left to talk about. Okay. I think we're going to leave part of this behind here because we'll get to it. All right. The debugging, we're going to be talking about this continuously, okay? Trying to use what they call the ping utility, right? To just check the connectivity. Uses a protocol called ICMP. We don't quite have enough time to deal with that properly right now, I'm afraid. All right, so we'll find a way to pick that up. But again, I think most of this should be familiar and we'll re-encounter it in practice as time goes on. But just, take a few minutes yourself to just review that quickly and see if it brings up any questions. And if it does, we'll deal with them when we're dealing with it in practice. All right. Let me just slip down here. All of these things are things that we can get to in due time. And even tomorrow, we'll see this one again when we talk about how we configure our network interfaces for smooth communication. So let's draw this to a close today, and we'll pick it up a little bit tomorrow, all right? And definitely by Thursday and moving on forward, all right, we will look at these things in practice and kind of pick it up from there. Turn off this and get it